Thousands of sun-tracking panels now carpet the American landscape, arranged in neat geometric rows that mimic the patterns of industrial agriculture. These facilities rely on a heavy industrial backbone. Beneath the glass, thousands of tons of steel and aluminum mounting structures support miles of subterranean wiring and specialized access roads. This is a semiconductor process. When particles of light, photons, strike the surface of a photovoltaic cell, they provide the energy to knock electrons loose from their atoms. This creates a continuous, one-way flow of electricity, known as direct current, or DC. Unlike concentrated solar power, which uses mirrors to generate heat and spin a mechanical turbine, photovoltaics convert sunlight into electricity using solid-state physics. There are no moving parts in the generation process itself. A utility-scale solar farm functions as an active industrial power station. It is a sprawling piece of infrastructure that physically redefines the land it occupies. To enter the grid, that power has to change shape. The direct current from the panels flows through heavy cables until it enters an on-site inverter. This device forces the current to rapidly switch directions, converting it into the alternating current, or AC, that powers our homes. Because the electricity must often travel hundreds of miles to reach a city, a transformer node then boosts the voltage, allowing the power to move across the landscape with minimal energy loss. This high-voltage power is then injected into the regional transmission grid, the massive interconnected network that balances electricity supply across entire continents. This chart explains the sudden ubiquity of these fields. Over the last 2 decades, the cost per watt of solar hardware has plummeted. As those manufacturing costs fell, the global capacity for solar energy spiked exponentially. This transition involves a massive industrial scale-up. Building these arrays requires significant material extraction, global manufacturing, and the acquisition of thousands of acres of land. We are faced with a new challenge: meeting our climate goals by moving our environmental footprint from the atmosphere down onto the Earth's surface. Arid desert landscapes are often the primary targets for large-scale solar development due to their high solar irradiance. However, research from the U.S. Geological Survey shows that fencing off these areas can disrupt wildlife corridors and sever the foraging routes of species like the desert tortoise. Biologists are also investigating the lake effect hypothesis. They suspect that migratory birds mistake the polarized light reflecting off vast panel arrays for bodies of water, leading to fatal impacts as they try to land on the glass. To reduce this pressure on wild habitats, some projects are being sited on pre-disturbed land, like capped landfills, former industrial brownfields, or floating on man-made reservoirs. Where a solar farm is placed is as environmentally consequential as the zero-carbon energy it produces. One attempt to resolve this land use conflict is agrivoltaics, the simultaneous use of a single plot of land for both energy generation and agriculture. In some climates, the shade from the panels keeps the ground cooler and helps plants retain moisture, while the plant's natural respiration cools the panels and increases their electrical output. This symbiosis has its limits. Staple crops like wheat require full sun and wide open spaces for heavy machinery, which the solar mounting structures physically block. Agrivoltaics is a series of trade-offs between crop yield and energy density, requiring engineering that is unique to every acre. Beyond the physical footprint, there is a systemic one. Solar generation is dictated by daylight and weather, but human energy consumption is driven by behavior, often peaking in the evening after the sun has set. While chemical batteries help bridge this gap, they are not a standalone solution for the entire grid. Storing enough energy to balance the variability of a multi-state system is a massive logistical and material hurdle. Traditional power plants provide physical stability through the inertia of heavy spinning turbines. Solar farms must replace this with grid-forming inverters, complex electronics that digitally stabilize the grid's frequency. Managing this requires advanced forecasting and flexible demand systems, allowing utilities to adjust how the grid operates in real time as the clouds move. Harvesting sunlight requires redesigning the entire philosophy of the transmission grid, rather than just plugging new panels into old wires. We also have to account for the clock. Most modern photovoltaic panels are designed for a 25 to 30-year life cycle. After decades of exposure to the elements, their chemical components degrade, and they are taken offline. While the glass, aluminum, and silicon are technically recoverable, The specialized recycling infrastructure needed to process millions of decommissioned panels is still in its infancy. Without that infrastructure, the solar transition remains a linear process, moving materials from a mine to a field and eventually to a landfill. This transition is a massive industrial undertaking. Its success depends on how carefully we integrate these heavy tools into the physical world they are meant to save. The challenge of the coming decades is not just engineering better ways to capture the sunlight, but intelligently redesigning the earth beneath the panels.